So before we get off and running into the webinar, a couple of further housekeeping slides. So here's our accreditation slide for those of you that are looking for the PDHs. Here is the information on the material being copyrighted. Again, if it is something that you would like a copy of, you can contact Miranda. We can get you a PDF of the presentation. And now on to the purpose and the learning objectives. I'm going to skip over the purpose. I'm just going to jump down to the learning objectives. This is really what we're looking at today. So upon completion of this seminar, you will be able to describe the process of combustion to include the effects of using the various fuels, natural gas, propane, or oil. Explain excess air as related to the combustion process, including its effect on sensible heat loss. Describe the relationship between excess air, CO2 level, and O2 level. Explain the relationship between excess air and dew point, and finally describe under what conditions NOx is formed and how it can be controlled. Now this topic here about combustion, this is always an interesting one. You know, you think about it, being the father of an Eagle Scout, I can tell you combustion is a very simple process that the boys always had no problem mastering it. But when it really comes to controlling it and pulling the most energy out of it, it's one that we do have to pay attention to. So what we're going to do is we're going to start from the basics and we'll work ourselves to the more complicated. Yeah. I think if you look at the slide on the right-hand side, the combustion triangle, that's something that probably everybody's familiar with. But when we're looking at combustion, we're really looking at an oxidation process. So it's a high-speed oxidation process. And the key for us is it generates light and it generates heat. And our goal is to take that heat that's being generated, harvest the heat, and put it into our application. Now, why it's described as a triangle is there's three things that are needed for the process to happen. I need oxygen, I need heat, and I need fuel. I have those together and in the right combinations, and then I can get this combustion process to happen and pull that energy out of it. Let's take a look at each one of the components before we move into the more complicated. So let's start off with the heat. And again, I'm actually going to jump to the bottom of the slide and work my way to the top. Typically, with most condensing boilers nowadays, everybody tends to use electronic spark ignition. What's good about that spark is the electric spark has a temperature of about 3,000 degrees. So if I look at that electric spark temperature versus the burn point of my various fuels, natural gas at 1100, propane at 875, atomized oil at 495, the spark provides us a hot enough temperature to get our fuel to burn. Now you'll notice carbon monoxide shows up there as well. Tend to throw that in there just as a reminder that it will burn if I am producing it in the process. So the spark provides the heat for the ignition, and then once the fuel is ignited, the heat from the combustion process then will continue to support the combustion process from the fire triangle side of things. So I have ignition. The next thing I need is I need the fuel. So the fuel side of my triangle. Now the fuels we use are all going to be hydrocarbons. So they're going to be molecules made up of carbon and hydrogen, and there's going to be different combinations. So here we see methane, which is the major component of natural gas. Then I show the hydrocarbon for propane, and then on the bottom is the molecule for fuel oil. The more carbon in the fuel, the higher the calorific value or the heat content. For instance, if I look at my two gaseous fuels, methane with a simple carbon and 4 hydrogen molecule, if I have a cubic foot of methane, I have about 1,000 BTUs of energy. I move over to the bigger molecule of propane. One molecule of propane will have about 2,400 to 2,500 BTUs of energy in a cubic foot. So, when I get to the higher carbon content, I end up with a higher energy content as well. But I have my heat, I have my fuel, and then I need my oxygen, okay? So my oxygen is going to come from the oxygen that's air, my combustion air. I'll bring that into the boiler and I'll utilize this as the third leg of my combustion triangle. Now, there's my composition of air. Air is about 21% oxygen. It's about 79% other gases. So that's going to give me the oxygen that's necessary to burn my fuel. But when we start to look at the effective way or the efficient way of burning fuel and extracting heat, everything that's in the air enters my combustion chamber, gets heated, and leaves the boiler. So when we start to look at air in that process, I have to be very concerned about how much air is going through, because I heat all of these, in the combustion process, I heat all of these molecules. The goal is to pull the energy out of these molecules, but what will happen is they also will carry energy away because I'm probably not getting them back down to the temperature that they came in. So it's almost a necessary evil in the process, because I need that oxygen to get my combustion. So if I throw it all together, I have my combustion process. So on the left-hand side, I have my fuel and my oxygen, my air. So we'll look at it from the aspect of natural gas, because that tends to be where the bulk of the business is right now. So for natural gas, I'll show it as a methane molecule. There's my carbon and hydrogen. Underneath there, I have my air, and it's being represented by oxygen and nitrogen. The molecules that I need are the oxygen molecules. Goes into the combustion chamber, I add the heat. When I heat it, I cause that high-speed oxidation, that burning to occur. What's coming out of that burning is some light and some heat. Again, the heat is what I'm interested in. And then I have my combustion gases. Among my combustion gases, I have my combustion products. What is the actual outcome, or the products of that combustion process? I'm going to end up with carbon dioxide, and I'm going to end up in water vapor. Now, what's key about this, when we start to look at measurement, and this will come into play later in the discussion, when I burn my natural gas, if I burn a molecule, I will always get a set amount of combustion products. So 1 molecule of methane gives me 1 molecule of carbon dioxide, and gives me 2 molecules of water vapor. And down the road, those 2 molecules are the ones that I'm going to be concerned with as far as measurement and also extracting the energy. Again, on the air side of things, the nitrogen entered into the combustion chamber, it got heated, and then it leaves the boiler after going through the heat exchanger of the boiler. So that nitrogen, think of it as being along for the ride, carrying the energy, but potentially as an energy loss as it carries that heat out when it exits the boiler and heads out the chimney. Okay. Now, the question becomes, in a controlled process, if I do a bonfire, I'm not really concerned about the air to gas ratio. Nature figures that out. But because of the fact that I'm now trying to do this as a controlled process, I have to look at controlling the process, and what I'm really trying to control is how much air is passing through. I know how much gas is going to pass through the combustion chamber because that's set by the firing rate of the boiler. If I'm doing a 1,000,000 BTU boiler, I need a certain amount of natural gas to get 1,000,000 BTUs. But for clean combustion, I have to figure out how much air I need to make this process that you see on the screen happen. This complete combustion that produces carbon dioxide and produces water vapor. Okay. This slide's a slightly busy slide, so I'm going to kind of talk about where I want to start. And I actually want to start here in the middle, where it says EG. Now, when I look at combustion, and I look at my fuel types, because of the fact that I need a certain amount of air to burn a certain amount of fuel, I can always look at it as a ratio, an air to gas ratio for complete combustion. So for instance, if I look at that first line in light blue, if I burn 1 part of natural gas, let's call it 1 cubic foot of natural gas, I need 10 cubic feet of air. It's a 10-to-1 ratio to provide me with the right amount of oxygen to completely burn my fuel. If I'm doing propane, I move down to the gray line. I need 25 parts of air for every 1 part of propane. It's a bigger hydrocarbon chain. And then if I jump down to the lavender, purple, plum, we'll go plum. The plum, if I'm burning oil, for 1 gallon of oil, I need 1,344 cubic feet of air to provide the right amount of oxygen to make that combustion process happen. This process of this exact match is referred to as stoichiometric. It's the theoretical perfect air-fuel mixture that will give me good, clean combustion and will give me complete combustion of my fuel. Now I'm actually going to jump back a slide and then come back around again. Under those conditions, you'll notice on this here, back to my, for my natural gas, my ratios. One molecule of natural gas gives me 1 molecule of carbon dioxide and 2 molecules of water vapor. These happen at set ratios. So when I look at combustion, and I look at how much air is coming in for that combustion process, I can look at carbon dioxide and use that as a gauge of what my air to gas ratio is for the combustion process. In that if I have stoichiometric or perfect combustion, I will have, for instance, with natural gas, I will have the CO2 will be about 11.9% of my combustion gases. If I'm burning propane, the CO2 is going to be about 13.7% of the combustion gases. Number 2, fuel oil is going to be about 15.5% CO2. These numbers represent the theoretical maximum CO2 numbers that I can achieve with each one of these fuels in the combustion process. Okay? Now, from a measurement standpoint, we often talk about the combustion process as being measured in CO2 as far as the quality of the combustion. The other one you may hear about is O2 or oxygen, okay? Now, if I jump back to the previous slide, you'll notice there are no free oxygen molecules on the combustion gas side of things. So in perfect combustion, all of the oxygen or all of the O2 is consumed, so it should show up as a 0 value. By having that 0 value for oxygen, I'll go with natural gas, by having that 0 value for oxygen or this 11.9 value for carbon dioxide, this will allow me to look at the combustion process and see where I am from a standpoint of how much air is in the process. Later on, we're going to talk about a term called excess air, but this becomes a great measurement device to look at it from the aspect of excess air from the combustion standpoint. So, a theoretical world. I have stoichiometric combustion. And we talk about it being about it, I say for this presentation, I'm talking about the ratio between natural gas and air to be about a 10-to-1 ratio. 10 parts air to 1 part natural gas or fuel. Now you'll notice in this slide, underneath the 10, I should say right next to the 10 parts air, in parentheses, I have this word about. If you go and you look online and you search out air to gas ratio for natural gas, you will find 10-to-1. You will find 9.5-to-1. You will find 9-to-1. You may also find 10.5-to-1. The number, there's a band or a range with this number. And where that range comes into play and where burner setup comes into play is in the real world, it's very difficult to maintain the air to fuel ratio at this stoichiometric number. There are things that change that can possibly change the combustion process. We're going to look at a couple of examples. So let's look at our fuel. We'll actually look at our fuel and we'll look at our air. So on the fuel side, actually, let's talk about the reason why. So the reason why I am concerned about this air to fuel ratio is I want complete combustion. I don't want to run oxygen deficient or fuel rich where I don't have enough oxygen for complete combustion. If that happens, if I have insufficient air, you'll find that I'm not going to be able to fully combust my fuel to produce carbon dioxide. I'm going to have some incomplete combustion that forms carbon monoxide, and carbon monoxide is a poisonous gas. There is health risks associated with it. So when we look at this, one of the goals in setting up the burner for combustion is to avoid making carbon monoxide. Okay? Now, where my variations can happen is, let's take a look at fuel. You know, whenever we talk about natural gas, everybody talks about it and they show the molecule for methane, CH4. The reality is, if you look at natural gas, it's not a pure methane gas. It's a mixture of gases. So on this chart here, it has a typical analysis, where the average numbers would be for natural gas, but then we also have a range to the right. So for instance, if I look at typical natural gas, methane makes up about 93.9% of that natural gas. However, the range for methane is anywhere from 87 to 97%. One of the other prevalent gases in natural gas is ethane. It's also a hydrocarbon. It makes up about 4.2%, but it has a range from about 1.9 to 9%. And then finally, we have propane. That also exists in natural gas. It has a typical percentage of about 0.3, and its range is about 0.1 to 1.5. So you have these various components with a range of concentration, which tends to make the calorific or the heat value change. And when that heat value changes, the amount of air necessary to burn it changes as well. Again, from an aspect of methane, if it's pure methane, my air to gas is about a 10-to-1 ratio. When I start looking at propane, I'm at 25-to-1 ratio of how much air I need. So when my fuel changes, the combustion process changes. The need for air to combust my fuel changes as well. Now, the thing is, it's not just happening on the fuel side, it also happens on the air side. This is a chart I happened to pull off of engineeringtoolbox.com. They have great things on there. But what happens is air is consistent in its percentage, where if I look at air is going to be about 21% oxygen. The problem is the density of the air can change. And one of the things that can change that density for this example is the temperature. So as the air temperature changes, the density of the air changes. So for as an example, if I have an outside temperature of 10 degrees Fahrenheit, my air, the density of the air will be about 0.085 pounds per cubic foot. And of that 0.85, 21% of that is oxygen. If I take that air and I heat it up to 70 degrees, at 70 degrees, the density has dropped down to a 0.075. So I've lost 0.01 pounds mass of molecules in that air when that temperature changes. If the density of the air changes, the density of the oxygen changes. The amount of oxygen available to combust my fuel changes as well. So I have both of my fuel and my air on their own changing, but also other things can happen. Furnace pressure, draft pressure, fan contamination, atmospheric pressure changing. Anything that changes the air or the gas can change the combustion process. And from an aspect of safety, I don't want to make carbon monoxide, and from an efficiency standpoint, I don't want to make soot. So typically when we look at the combustion process, we have our fire triangle to support combustion. We know how much air is needed to burn the fuel, but what we want to do is we want to apply what's called excess air. And excess air is added to the amount of air needed for combustion to ensure if there's any variations, I stay on the safe side of combustion. I stay on the side of complete combustion. What you'll have is you'll have your fuel, you'll have the air to support combustion, but then you'll add excess air as well. Typically somewhere between about 17 to 30%. 17 actually may be on the low side looking at actual applications with a lot of boilers. So why do we do this? It becomes a balancing act. If I have too little excess air, my safety margin away from complete combustion and into incomplete combustion becomes minimal, and I worry about making carbon monoxide and I'm making soot. Okay? On the flip side, I don't want to have too much excess air because excess air wastes energy. Okay? Think about this excess air. It doesn't participate in the combustion process. It doesn't generate any heat, but it has to be heated when it enters the combustion chamber. So it picks up heat. It's now extra molecules moving through my combustion zone, moving to my heat exchanger, and then moving out the boiler vent. Whatever that extra air leaves, whatever temperature it's leaving at, represents lost sensible heat. So it becomes a balancing act to drive that efficiency. And again, typically, it says we may drop down to 17%. On the high side, probably 30. In most cases, I'm going to say we're probably a little bit more tighter than that, probably maybe 20 to 30%. Okay, so I add this excess air in. And by having the excess air, it keeps me safe. Okay. So if I look at my process here, I have my fuel, natural gas. I have the air necessary for the combustion process. I add in my excess air. The excess air now comes into play. It comes into play from the aspect of it now has to pass through the combustion chamber. Okay, so I pass it through the combustion chamber. I still get carbon dioxide. I still get water vapor. I still have the nitrogens that are transported because of the air needed to support combustion. But now this excess air now continues through, and what I'm bringing into the boiler pretty much exits the boiler. I have more nitrogen. Now notice in here, all of a sudden on the right-hand side, the flue product side of things, now oxygen is starting to appear. So when I start to add excess air, I start to see oxygen as something in my combustion gases, which now, again, lets me utilize the amount of oxygen being measured to figure out how much excess air is being added to the combustion process by measuring oxygen, okay? Now, the other thing that happens, we talked about combustion in terms of carbon dioxide, because the amount of carbon dioxide that I form is really based on how much fuel I'm burning. So this is a fixed quantity. As I start to add excess air, that fixed quantity now as a percentage of all the combustion gases become less. So what you'll find is as I add excess air, carbon dioxide starts to drop. The carbon dioxide percentage starts to drop. So we can use that as an indicator of how much excess air I have. So again, excess air, good for the process. I can measure it by looking at how much oxygen is in the combustion gases. The more oxygen, the more excess air. I can also measure it through carbon dioxide. As the excess air increases, the percent of carbon dioxide drops as well. So where do I want to be? From an excess air standpoint, back to my 17 to 30%. That's a good, safe value to operate. If I'm measuring it through oxygen, I expect the oxygen to represent about 3 to 5% of the combustion gases. If I am measuring it through carbon dioxide, now I'm down to a range of about 8.5 to 10%. And remember, perfect combustion was about 11.9. Let's call it 12%. So more excess air, I'm dropped from 12% down to this lower band of 8.5 to 10%. If I'm looking at propane, I'm down to 10.7 to about 11.1. If I'm burning number 2 fuel oil, I expect to see somewhere between 12.1 to 12.7. But this becomes the point for excess air to support my combustion triangle for good, safe combustion that's both safe and efficient. Okay. Now, the final part of the combustion process. Okay? We talked about the fire triangle. We talked about adding excess air. Now it's about really the combustion process itself, the dynamics of the boiler. Okay? We got another 3, and you'll hear them referred to as the 3 T's of combustion. These look at how I'm burning the fuel to make the combustion process as efficient as possible. And this is about clean combustion. Okay, so if I look at burning, and 3 T's are really about the dynamics of the combustion chamber, the burner assembly, and with a premix burner, the actual burner itself, the full components. Okay. And it's about getting giving the fuel, the air, and the heat the ability to cause that combustion to happen cleanly. The first of my 3 T's is temperature. excuse me, I have to make sure the temperature surrounding the flame will be hot enough to support clean combustion. In most premix burners, it's not an issue because of the design. Realistically, where the temperature tends to come into play is if I'm doing a power-fired burner with essentially one long flame. I have to make sure that not just in the core of the flame is hot enough, but the outer envelope is as well to see that combustion. But if I don't have good temperature, not just in the core, but on the other outer envelope of the flame, then I won't have good, clean combustion. The next T is time, okay? Combustion takes time. So the dynamics of the length of the flame, the combustion chamber has to everything has to be designed that I have sufficient time for the fuel to fully combust within that combustion chamber. Okay? Now, the final one is turbulence. Okay? Think of turbulence as mixing. Okay? And most people, when they think of turbulence, they think of that picture in the middle showing the burner head of a power-fired burner. So in here, the turbulence happens within the combustion zone. I'm going to have a diffuser or a baffle on the burner assembly that will generate movement in my air, and that movement in the air combined with the nozzle inside that burner will ensure that I get good mixing of my air and my fuel so that the oxygen and the fuel are mixed so that I'll have good, clean combustion. When I get to a pre-fired burner really is about drawing, here it is, here's the blower assembly, here's the gas valve, right here is my venturi. So as the air passes through, the venturi draws the natural gas or the propane through the gas valve into the airflow. That airflow enters into the blower. In the blower, the movement of the blower mixes the air and the gas together, and then they pass into the burner assembly, and then through this turbulence that happens over the entire process, I have good mixing of the air and gas, which will give me the turbulence that gives me good, clean combustion. But from a burner design, burner combustion chamber design, if I expect to have good, clean combustion, we have to take a look at the temperature, the time, and the turbulence to ensure that I have everything necessary to produce good, clean combustion. So, kind of a quick midpoint summary. From an aspect of combustion, we talked about the fire triangle. What's necessary from a basic standpoint to get a fuel to burn. Then we looked at how much air is necessary from the aspect of getting complete combustion of the fuel, but also talked about excess air. How much air do I have to make sure that my combustion process stays clean and I don't form carbon monoxide, but I'm also efficient. And then finally, we looked at the 3 T's of combustion. Okay, let's take it into the combustion chamber, into the burner assembly, and what's necessary to get that combustion, again, to burn cleanly. Now, I think we're at the point, let's take a look and see if we have any questions. Oh, we have no open questions. Okay, so I think we will move onward from here. Okay, so now that I have burned my fuel, now comes the question about, where is the energy, and what am I doing to extract that energy? So when I look at that combustion process, while I'm producing molecules of combustion gases and my excess air is passing through, typically when I look at the heat that's generated, the energy that's generated, it really comes down to, if I will, 2 types of energy that happens in that combustion process. Okay? Now, the first one is what's referred to as sensible heat. It's referred to as sensible because it's something you can measure or you can feel by a change in temperature. So I burn my fuel, let's say the fuel burns at 3,000 degrees, 2,800 degrees. That temperature represents sensible heat. That temperature normally is also deposited in all of the molecules that are passing through the combustion zone. Now I start to draw the temperature of my combustion gases down. As I draw that combustion gas temperature down, I'm pulling back that sensible heat. That represents about 90% of the energy. This is why when you look at non-condensing boilers, you see efficiencies of 80 or 83 or 85, or some of these near condensing boilers with the efficiencies of maybe 87 or 88%. Again, all of these numbers are natural gas numbers. It's because with a non-condensing boiler, I am working on about 90% of the energy that's being generated in the combustion process. The other 10% is what's referred to as latent heat. And latent is Latin for hidden heat, okay? It's heat that's you can't measure with a drop in temperature. It's actually heat that's tied up in water vapor. Now let's take a look at our combustion products again, okay? So if I look at my combustion process, and I'm gonna look at the flue gas side of things, I have all of these molecules that have passed through the combustion zone and picked up heat. And all of these molecules, the temperature of the molecules, this is all sensible heat. So carbon dioxide, water vapor, nitrogens, all of these gas molecules will contain heat from the combustion products. What I'm doing when I'm trying to extract that heat is I'm trying to drop all molecule temperatures down, pulling that heat out. Now, the other thing that I have in there is my water vapor. When I talk about latent heat is about water vapor, okay? It's not about a drop in temperature. With latent heat, we're talking about a phase change. From the combustion process, this water vapor exists as a vapor inside the combustion chamber. When I'm trying to harvest it, I have to do a phase change. I have to change the vapor from a vapor to a liquid. And that's where this hidden or this latent heat comes from. Okay. So within the boiler, I have the water vapor. That's one of my combustion gases. It exists as a vapor. I want to change it from a vapor to a liquid. And when I change it from a vapor to a liquid, I release the latent heat, the heat of vaporization or the condensation, if you will, that's tied up in that molecule existing as a vapor. Okay. Now, question comes up is how much energy can I release? Well, if I look at the condensate that's coming out of a boiler, for every gallon of condensate that's coming out of that boiler, it's being formed in the boiler, that's about 8,100 BTUs of energy that would have gone up the chimney. So when I do a condensing boiler and I look at the energy that's being formed in this combustion process, it's all about pulling in the sensible heat, but it's also about pulling in the latent heat. And that's where I start to build my efficiency. Okay. Now, the question becomes, some boilers condense, some boilers don't. Some are designed not to condense. And the question becomes, how much condensate can I get, or how can I get that boiler to condense? It's all about what's called the flue gas dew point. Think of that as one of my determination of whether the boiler condenses or does not condense. By definition, a dew point is the temperature to which a parcel of gas or parcel of air must be cooled in order for the water vapor to be condensed to water. Okay? So that's the book definition. It happens in the boiler, it happens outside, particularly on humid mornings. But what happens is if I look at my combustion gases, there's going to be a temperature that when those combustion gases get below this dew point, the condensing process starts to happen, and I can start to pull back some of this latent heat. Okay. Now, the key when I start to look at this process happening, this dew point, which will be the trigger point for the condensing to occur, it's not a set number. A lot of times when you look at projects and people talk about projects and how they're going to perform, they immediately say, well, the return water temperature is going to be below 130 degrees. The boiler is going to condense and we're going to get good performance out of it. The thing with condensing is the dew point is not a fixed temperature that's locked in and it's always going to perform at that number. The dew point is actually a moving target that's tied to how well my combustion process is set up. And really, we're looking at it from the aspect of how much excess air is in the combustion process. Okay. If I look at the combustion, let's see, I'm going to back up here. I hate to do that, but if I look at the combustion process, we talked about carbon dioxide being formed at a fixed amount for the fuel I'm burning. So 1 molecule of carbon dioxide gets me 1 molecule of methane gives me 1 molecule of carbon dioxide. Same thing happens with water vapor. 1 molecule of methane gives me 2 molecules of water vapor. So there's a fixed amount of water vapor being formed based on the amount of fuel that I'm burning. Okay? Now, if we keep that thought in mind, if I look at my stoichiometric, my perfect combustion, 1 part natural gas, 10 parts air, that produces a certain amount of combustion gases. The water vapor represents a certain percentage, just as the carbon dioxide represents a certain percentage of my combustion gases, or my flue gases. The thing with water vapor, as I drop CO2, water vapor and CO2 essentially are linked together. When the percentage of carbon dioxide drops, the percentage of water vapor drops with it. As water vapor becomes a smaller percentage of all the flue gases, by dropping the percentage of the water vapor, it becomes more difficult to get the boiler to condense. I have to go to a lower return water temperature. So when I look at the boiler as a condensing device and looking at my combustion side of things, if I add excess air, the CO2 lowers. Okay? If the CO2 percentage drops, the water vapor percentage in that flue gas drops as well. And if I drop the water vapor percentage, that means the dew point has to drop. So although everybody talks about the point of condensing, or the dew point being 130 degrees Fahrenheit, the reality is it becomes a moving target. So this chart here shows me the relationship between excess air as displayed as CO2 percentage in my combustion gases versus the dew point of the water vapor. So if I'm starting off with, say, on the high end of that band that we talked about earlier, I'm at 10% CO2. At 10% CO2, my dew point's about 133 degrees Fahrenheit. So that becomes my crossover between non-condensing and condensing. If my flue gas temperature stays above 133, the boiler doesn't condense. I don't achieve high efficiencies. If the return water temperature dips below 133, now all of a sudden the boiler starts to condense. And the lower the return water temperature goes, the higher the efficiency will be. But if I have that burner set up not at 10% CO2, if I increase my excess air, my CO2 is going to drop. Let's say I drop it all the way down to 8%. At 8% CO2 with that increased excess air, now my dew point is down to 122 degrees Fahrenheit. All of a sudden, I have this band here now. If I look at the space between, and that area there at 10% CO2, the boiler would have been condensing, but now it's not. So I have a lower dew point. I end up with having to go to a lower temperature to get the boiler to condense, and it produces less condensate. The efficiency is lower. So when I start to look at driving efficiency, excess air and burner setup really plays a large factor in a couple of different areas. So from an efficiency standpoint, where should I be? From an excess air, I'd like to be, actually, let's tighten it up a bit. Let's say somewhere between 25 to 30% excess air. If I'm looking at this measuring from a CO2 standpoint, that's about, let's call it 8.5 to maybe 10% CO2. as measured at the boiler. Okay. I want to have a fully modulating input. Okay. Now, we really didn't talk about this, but when I look at boiler efficiency, one of the losses that I see in the system is if the boiler is going to have to cycle, turn off and on, because the boiler and the system, I can't match the output of the boiler to the load of the system. If the boiler is fully modulating, not stepped, I can do a better job of matching the output to the load, which will reduce my hunting and also reduce my cycling. I'm going to run more efficiently. Finally, I'd like precise calibration through the entire firing range. What that really means is high fire to low fire, I want to be consistent in my excess air. I want my CO2 to be close high fire to low fire. Now, what do we mean by that, or how does that show up? This happens to be looking at a burner setup for a boiler. And it's showing a series of boilers. And it's showing where I'd like my carbon dioxide to be at high fire and low fire. So if I look at my natural gas numbers, at high fire, I want to be at about 8.9%, somewhere in the middle of that band we discussed. At low fire, I'm looking at about 8.5%, very little fall off, which means from an aspect of combustion, my excess air is fairly consistent, or very consistent from high fire to low fire, which means my performance stays consistent from high fire to low fire. Okay, this happens to be from another boiler manufacturer and another setup. And if you look at it here, at high fire, the CO2 level is about the same as you see here, at about 8.9. But at low fire, we're looking at a CO2 level of about 2.8. Dramatic fall off from high fire to low fire. Differences between the two is a 5-to-1 turn down boiler. This happens to be a 25-to-1 turn down. A lot of times the question is, well, how does that happen, or why does that happen? Let's take a look at the combustion process and look at it from the aspect of what's needed for good, clean combustion and everything we've talked about so far. So if I say, okay, let's take a 1,000,000 BTU boiler, and let's look at the makeup of the air-gas mixture going into the burner assembly. For 1,000,000 BTUs an hour boiler, I need about 16.67 cubic feet per minute of natural gas being burned. In order to support that combustion, based on my 10-to-1 based on my 10-to-1 ratio between my fuel and my air, that means I need about 166.7 cubic feet per minute of air to support the combustion. If I want 30%, I need to add 30% more for safety. That gives me 50 cubic feet per minute of excess air, or a grand total of 233.37 cubic feet per minute entering that burner assembly. Under those conditions, I end up with a consistent flame pattern that's designed to support, through the 3 T's, combustion in that chamber. Additionally, what helps keep the burner mesh assembly cool, if you will, is the movement of this air-gas mixture through the burner assembly. As it enters in there, it helps keep the burner assembly cool. Okay? Now, when I do the 5-to-1 turn down, all of a sudden my numbers start to drop by a factor of 5. My combustion gases, my natural gas drops down to 3.33 cubic feet per minute. My air needed for combustion drops down to 33.3, and my excess air drops down to 10 cubic feet per minute, for a total volumetric flow of air-gas mixture of 46.6 cubic feet per minute. However, at a 5-to-1, if you look at what's happening, that the flame pattern around just shrinks down, but I still have enough turbulence for clean combustion. I still have enough throughput of air-gas mixture to maintain my flame pattern and maintain coolness on my combustion head. Let's take a look at what happens if I move up to 25-to-1. Okay, I'm going to keep my high fire numbers up there. But let's throw the low fire at 25-to-1. At 25-to-1, my natural gas needed to support low fire now becomes 0.67 cubic feet per minute. the air needed to support combustion becomes 6.7 cubic feet per minute. And if I maintain consistent high fire to low fire excess air, I'm down to 2 cubic feet per minute for a grand total of 9.37. All of a sudden, the volumetric flow through everything starts to drop. I may not see good turbulence and good mixing through the blower assembly. I probably don't have enough volumetric flow through the burner assembly to support a good flame pattern all the way around the outside, and my combustion becomes, I guess I'll use the term sketchy, very sketchy. So what can I do to maintain volumetric flow rate? Well, one thing I do know is if I'm going to do a 25-to-1 turn down, I got to maintain, I'm trying to get down truly to 4% input. I only need 0.67 cubic feet per minute of natural gas. And to support that side of things, I only need 6.7 cubic feet per minute of air to maintain combustion. So what I can do is I can increase my excess air, okay? Now this is probably a little bit extreme, coming back up to a 5-to-1 turn down, probably could get by with maybe a 7 or an 8-to-1 total flow rate. But if I'm saying, you know what, I know 5-to-1 is going to work for me, so I'm going to bring my volumetric flow back up to the 5-to-1 number. I need 46.6 cubic feet per minute passing through that blower assembly. So all of a sudden, my excess air has to change from 2 CFM to 39 CFM. I have significant excess air coming through here. Really, I've really gone beyond the 200% number. Okay. The question becomes, now at low fire, with a significant increase in excess air, I don't have consistency now from high to fire to low fire. What happens? First off, from the sensible side of things, if I've dramatically increased my excess air, all of a sudden my sensible losses are going to come up dramatically because of all of these extra molecules just passing through and pulling that heat along through the process. Additionally, the other thing that happens is it significantly impacts the boiler's ability to condense. So here it is at 9%. My dew point is about 129, 128 degrees Fahrenheit. At low fire, and let's call it 3% excess air, means 3% O2, my dew point now is down in the neighborhood about 92 degrees. So by not maintaining consistency from high fire to low fire, my sensible losses go up and my latent gains go down considerably because of how this excess air affects the dynamics of that heat recovery. Okay, so the question often comes up from a boiler design standpoint. We're going to kind of cross over in a little bit of boiler design. From an aspect of burner design, 5-to-1 always becomes a nice safe number when we're looking at consistency from high fire to low fire. So the question becomes, well, if I'm looking at how to approach it from a safe side, from the consistency from high fire to low fire, how do I deal with cycling losses without that large turn down? One of the things you will find, and this is fairly consistent in the industry, we're starting to see a lot of large mass or large water content boilers make their way into the market. This large water content gives us a thermal battery, if you will, to put energy into as the boiler's running if I can't match the output of the burner to the load of the system on the shoulder seasons. It keeps the burner running for a long period of time, reduces the cycling. Additionally, the large water content can act as a thermal battery, and that when the burner shuts down, I can extract the energy out of that boiler to give me a long off cycle. The other thing that you can do from a boiler design is I can go to multiple burners. By going to multiple burners, I can increase the turn down ratio beyond 5-to-1 and still not have any one individual burner exceed that 5-to-1. But with these kind of applications, I can meet my requirements from a design standpoint, particularly my precise calibration through the entire firing range. All right, let's see if we got any other questions at this point. Question and answer bin is still empty. All right, and we might even finish on time. Now, as the slide says, is there anything else to consider? And the answer absolutely is yes, and it's not nationwide, it's more almost up from a pocketed standpoint. And the consideration is really about the other combustion gases, okay? And one in particular, and you'll hear more and more people talking about NOx level or NOx emissions. So here's the EPA's technical bulletin on it. And I'm going to just read the first and the last line here. Nitrogen oxides are a family of poisonous, highly reactive gases. And the last one, it's a strong oxidizing agent and plays a major role in atmospheric reactions with volatile organic compounds, often referred to as VOCs, that produce ozone on hot summer days. So when we start to look at different areas of the country, and in areas particularly where they're worried about smog and certain gases getting into the atmosphere, there's becoming more conversations about NOx emissions. And typically how that's going to show up is they're going to call for probably 20 ppm NOx at 3% O2 is probably a typical specification that we see from the NOx side of things. So let's take a look at where this NOx comes from and how we can control it. Okay? So back to our talking about combustion, a little bit different graphics here, but kind of pretty much the same story. So here I have my air-fuel mixture. And up in the top here, that's the air-fuel mixture to achieve my 10-to-1 ratio for combustion. Here's my excess air that I'm going to add into the process to make sure I have don't form carbon dioxide or soot in the boiler. I burn my fuel, okay? And here's things that we've talked about before: water vapor, carbon dioxide, and nitrogen. But now we're starting to see, here we have an NO, here we have another NO, here we have an NO2. Now we're starting to talk about nitrogen oxides working into the process. Okay, so in the nitrogen oxide world, there are really two major players in the nitrogen oxide world. Okay, first one is nitric oxide, or NO. Okay, and NO is formed in the combustion process when I bring up my combustion gas is hot enough and I have enough excess air that I have enough oxygen available that this process can occur. And it has to be at a fairly high temperature. So I have nitrogens, I have oxygen in my combustion process, I have a high temperature. It will combine to form nitrogen oxides, and that becomes part of my combustion gases. Okay. Now the other one is nitrogen dioxides. Nitrogen dioxides form with my nitrogen oxides. Don't show it here, but in the entire process of going to smog, it also includes volatile organic compounds. If I take my nitrogen oxides, I take oxygen, I add in the heat of the sun, I'll form nitrogen dioxide, and then I have one of my precursors for smog. So from an aspect of control, it's all about controlling this process in the top here. And I'm trying to stop the formation of nitric oxide that will eventually lead to the formation of smog in my air, or ozone. Okay. So a couple of things that come into play. For NOx formation, it's very simple about what we're looking at from a combustion standpoint. In order for it to form at a high rate where we have to be concerned, my flame temperature has to be above 2,800 degrees Fahrenheit. That's one of the key factors in NOx formation. The other one is my excess air has to be about between the range of 25 to 45%. So I brought this chart over here showing my O2 level, excess air, and CO2. Again, nice chart from Engineering Toolbox. But if I'm at 25% excess air, that's a an O2 level of about 3%. And with natural gas, you know, we're just shy, we're probably sitting just about at 10% CO2. If I'm at 45, you know, O2 is at about 6%. CO2 is about 8.5%. So you notice quickly looking at it from an aspect of CO2, perfect setup is right in the range for the excess air for NOx formation, okay? So, and it's trying to get my NOx formation down below acceptable levels, okay? The goal is from a burner setup or a burner design standpoint, in most cases, it becomes an idea of, okay, let's switch our target for carbon dioxide. If we're looking from an excess air standpoint, let's get our excess air greater than 45%. How do we do that? Let's make sure that our CO2, we shift our CO2 band down, that rather than having the high end, having the bottom end at 8.5%, the high end becomes 8.4. I get it down into this range, and what happens is everybody looks at that and says, wait a minute, that's going to put more oxygen into the process, which would tend, everybody would think would have it, we'd have a higher level of formation of NOx. But what this will do is by increasing the excess air, we start to knock down the flame or the combustion gas temperature. And by dropping the combustion gas temperatures down to an acceptable level, we then can reduce the rate of NOx formation. So I dropped the temperature down. Now I can get the NOx level to that 20 ppm or less range, which is the standard for most standards. Just a slide right in. So to bring it all back together, let's come back to our learning objectives. So I'm going to start at the bottom. We just described under what condition NOx is formed and how it can be controlled. If I move up there, previous to that, we just spent a pretty good amount of time talking about the relationship between excess air and dew point, excess air CO2 and O2. We explained excess air is related to the combustion process, including its effects on sensible heat. And then we described the process of combustion. So, covered a lot of ground in an hour. Let's see if there's, so there are still no open questions. So I guess right now I'm going to put it back out there. Right now, if there's any questions that anybody has, please ask them. We have a little bit of time left. I know we're just about on the hour, but always like to hear back from the group as far as what your questions are on the subject. Now I wish I had the Jeopardy music to play in the background. Well, if there are no questions, thank you all for coming, and hopefully you found the presentation informative. And hopefully we'll see you in the future for other presentations that we will be doing.